We're going to now look at section 8.4, Trigonometric Substitutions, which is going to rely heavily upon what we just covered in section 8.3. In example 4 of section 6.5, we wrote the arc length integral for the segment of the parabola y equals x squared on the interval 0, 2 as the integral from 0 to 2 of the square root of 1 plus 4x squared dx. At the time, we did not have the analytical methods needed to evaluate this integral. The difficulty is that the square root of a sum, or a difference, of two squares is not easily simplified. On the other hand, the square root of a product of two squares is easily simplified. For example, the square root of a squared plus b squared equals the absolute value of ab. If we could somehow replace 1 plus 4x squared with a product of squares, this integral might be easier to evaluate. The goal of this section is to introduce techniques that transform sums of squares and also the difference of squares into products of squares. Integrals similar to the arc length integral for the parabola arise in many different situations. For example, electrostatic, magnetic, and gravitational forces obey an inverse square law. Specifically, their strength is proportional to 1 over r squared, where r is a distance. It turns out that the integrals containing the terms a squared plus or minus x squared, or x squared minus a squared, where the a is a constant, can be simplified using somewhat unexpected substitutions involving trig functions. The new integrals produced by these substitutions are often trigonometric integrals of the variety studied in the preceding section. So let's look at our next example, example 2, doing a sign substitution. Here we're going to evaluate the integral of 1 over the quantity of 16 minus x squared to the 3/2 power dx. If you look at the denominator, you can see the factor inside of the parentheses, 16 minus x squared. This has the same form as a squared minus x squared that we've been looking at since the beginning of this section if we make a equal 4. So then we can use the substitution x equals 4 sine theta with dx equaling 4 cosine theta d theta, as we saw in the previous sections and examples, to simplify the denominator and the entire integral. So if we have 16 minus x squared, and we substitute in 4 sine theta for x, so we get 4 sine theta squared. Notice this is 16 times 1 minus sine squared, because 4 squared is 16, so we get 16 minus 16 sine squared theta. Factoring out the 16, we get 16 times 1 minus sine squared theta, which of course is cosine squared using the Pythagorean theorem. And then if we take the square root of 16, remember when you have a fraction exponent, the denominator is the root, the numerator is the exponent, if you will. So we're taking the square root of 16, which is 4, raised to the 3rd power. 4 to the 3rd power is 64. We're taking the square root of cosine squared. The square root of anything squared is just the base, cosine, and then that cosine raised to the 3rd power is cosine cubed. So the entire denominator simplifies to 64 times cosine cubed of theta. So we can rewrite our integral. Remember, our dx is 4 cosine theta d theta. That's in the numerator. We just simplified the denominator to 64 cosine cubed theta. Well, here we have a factor of cosine in the numerator and denominator, so we can cancel one of those out, and we get cosine squared in the denominator. And 4 over 64 becomes 1 over 16, which can come out in front since it's a multiplier or a constant multiplier. Well, 1 over cosine squared is the same as secant squared, the reciprocal identities from trigonometry. And the integral, or the antiderivative of secant squared, is tangent theta. So we get 1/16 times tangent theta plus the constant of integration for this. But wait, we're not done yet. Notice that we solved this in terms of theta, but the original problem was in terms of x. So we really need to express our result back in terms of x. One of the easiest ways to do this is by building a reference triangle. Since we know that we defined x as equal to 4 sine theta, then we know that the sine of theta equals x over 4, or opposite over hypotenuse. By that we can figure out the remaining side of the square root of the hypotenuse squared minus x squared, etc. So we've got this reference now. In our answer, we actually have the tangent of theta. So tangent is equal to opposite over adjacent. So we can go ahead and just, instead of just defining this in terms of theta and plugging in a value for theta that's in terms of x, we can actually plug in the tangent of theta. The tangent of theta is opposite over adjacent, or x over the square root of 16 minus x squared. So we can just plug this directly into our solution from before, which makes it really quite simple. So we get 1 over 16 times x over the square root of 16 minus x squared, which simplifies into this version here. And again, you see some extra related exercises to get a little more practice in this kind of concept. So now let's look at integrals involving a squared plus x squared, or x squared minus a squared. The additional trigonometric substitutions involving tangent and secant use a procedure similar to what we've already used for the sine substitution. The figures in the table below summarize the 3 basic trigonometric substitutions for real numbers where a is greater than 0. So this first diagram is the one we've been using, where we did a substitution of x equals a sine theta. And this you can see down here, the corresponding substitution that we did. And then, of course, we simplified it to change it from a difference to a product, and ultimately getting a squared cosine squared theta. When we have a squared plus x squared, we're going to use the substitution x equals a tangent theta. So when we have sine, it's minus, right? Sine is minus. When we have tangent, t is like a plus. So a squared plus x squared is like a plus, and that's tangent. X equals a tangent theta. And then you can see the process down here, the corresponding substitution, x equals a tangent theta. And then when we go through, we get that this whole substitution becomes a squared secant squared theta. And then finally, if we have x squared minus a squared, if the difference is changed order, we're going to have x equals a secant theta. You see the substitution down here in the table. And then the ultimate, when we plug that in, we get secant squared minus 1, which of course is tangent squared. Okay? So all 3 of these are going to work similarly, but with different substitutions. A squared minus x squared, x equals a sine theta. Sine is minus. A squared plus x squared, plus is like a t, and we're going to do the substitution x equals a tangent theta, the t there. And then finally, when the x squared is the difference, it has x squared in the front, then that's going to be x equals a secant theta, excuse me. And then you can see how these all revolve, how the identities come out to turn it into a product. But these are all Pythagorean identities that shouldn't be that difficult. So now let us look at example 3. This is the example we actually started the discussion in this section with, specifically finding the arc length of a parabola, or evaluating the integral from 0 to 2 of the square root of 1 plus 4x squared dx. Well, the first thing that we want to do is we want to simplify the integrand, or the integral, so that it looks like what we are. I'm going to try to find this pointer, sorry. There we go. So that we have one of the forms that we're looking for, a squared plus x squared minus a squared, or a squared minus x squared. Okay? So the first thing I'm going to do is factor out a 4 so that we get x squared alone. And notice that makes this 4 times the quantity of 1/4 plus x squared. Well, since it's a product now, I can take the square root of 4, which is 2, outside of the radical and also outside of the integral. That leaves us with 1/4 inside, and of course 1/4 equals 1/2 squared. So I can rewrite the original equation, the original expression, as the 2 times the integral from 0 to 2 of the square root of 1/2 squared plus x squared dx. Now we can see that this is in the form of a squared plus x squared. And remember, when we have the plus in the middle, this is plus like a t is tangent. So, and a is equal to 1/2. We can see that in the simplification that we did. So we're going to set x equal to 1/2 a tangent theta, or 1/2 tangent theta. And when we take the derivative of that, we get 1/2 secant squared theta d theta. So if we plug this in, specifically x equaling 1/2 tangent theta, we can see the reduction that happens with this whole radical. So we get 1/2 squared plus x squared. Substituting in 1/2 tangent theta, we get 1/4 plus 1/4 tangent squared. If we factor out that 1/4, we get 1/4 times the quantity of 1 plus tangent squared, all inside the radical. Well, the square root of 1/4 is the square root of 1 over the square root of 4, which is 1 over 2, which is what you see outside the radical here. So we get 1/2 times the square root of 1 plus tangent squared. Well, 1 plus tangent squared is an identity, the Pythagorean identity from trig, and so this equals secant squared, so we get 1/2 times the square root of secant squared. Well, the square root of secant squared is just secant. So this entire internal integrand becomes just 1/2 secant theta. Okay? So when we're integrating 2 times 1/2 secant theta, remember the dx becomes 1/2 secant squared theta, d theta. Simplifying that, we get 1/2 times 1/2 is 1/4. 1/4 times 2 is 1/2. 2/4 or 1/2. Secant times secant squared gives us secant cubed. So it looks like a much simpler integral, but of course we know from last section that these powers on trig functions are challenging, and so we had reduction formulas. Specifically, reduction formula for secant is here. Secant to the nth power x is equal to secant to the n minus 2 x tangent x over n minus 1 plus n minus 2 over n minus 1 times the integral of secant to the n minus 2 power x dx. And so this becomes simply 1/4 secant theta tangent theta, because 3 minus 1 is 2, and that comes out to the front, plus the natural log of secant theta tangent theta plus c. Okay, how do we get there? Because here we have 3 minus 2 is 1. 3 minus 1 is 2. That gives us 1/2 in front of the integral of just secant x. And the integral of secant x is simply that. The natural log of secant plus tangent. Okay. Of course, we're not done there, because again, we have to convert this back into x format by building our triangle. Okay. Again, we had x equals 1/2 tangent theta. So tangent theta equals 2x, and so that means that tangent theta is opposite over adjacent, so 2x over 1. And then we can figure out the hypotenuse here. So we have a value for tangent. We also need a value for secant, because that's in our final theta expression. Remember that secant is 1 over cosine. So this is hypotenuse over adjacent, square root of 1 plus 4x squared over 1. And so we can plug all of this in and get back to our final x value, and then we can plug in the limits of 0 and 2. You might notice here when we went from x values to theta values for the integral, we didn't convert the limits of integration. They could be a little bit more involved because they weren't exact, they weren't known angles, and we were dealing with secant and tangent, not sine and cosine, which tends to be a little bit easier. And so we just kept them off of the integral until the final step when we converted it back to x, and then we could just use the original values because these were values, limits are values for x. And so again, we just plugged in for secant, plugged in for tangent throughout the entire thing, and then simply used a calculator to come up with our final result here. Okay. Let's look at another example. Example 4 is another tangent substitution. Okay. So we have evaluate the integral of dx over 1 plus x squared squared. Again, we can see in here we have a squared plus x squared, which is a tangent, right? We have a plus, and that's our tangent, so we set a is going to be 1. 1 squared is 1. So we set x equals 1a tangent theta, or 1 tangent theta. And then, of course, if we take the derivative of both sides, we get dx equals secant squared theta d theta. Okay? If we substitute these two values in for dx, we have secant squared theta d theta. For 1 plus x squared, we get 1 plus tangent squared, which of course is secant squared. 1 plus tangent squared. 1 plus tangent squared equals secant squared, and then we square that so we get secant to the fourth. Secant squared over secant to the fourth gives us 1 over secant squared. And since secant is the reciprocal of cosine, 1 over secant squared will give us the integral of cosine squared. You might remember, again, we have this power of sine or cosine here. We had a way of reducing those, especially when it was an even sign, and that is that we use the half angle identity that cosine squared equals 1 plus 2 theta, cosine of 2 theta over 2. So we're going to convert this into a cosine integral without any powers on it. So this is equal to the integral of 1/2. This is just making this into two fractions, 1/2 plus 1/2 cosine 2 theta, or 1/2 plus cosine 2 theta over 2. We really probably should have done these as two separate integrals, just for clarity, and I didn't write that other integral symbol in there. So the integral of 1/2 is simply 1/2 times theta. The integral of cosine of 1/2 cosine 2 theta is simply sine of 2 theta over 4 plus the integral of the constant of integration, excuse me. Okay. Now we have to convert back to x. Now, so far we've been able to just use build a triangle based upon our original substitution, tangent theta equals x. So that means that tangent of theta equals opposite over adjacent, x over 1, so we can build that side and then build the hypotenuse. Okay. Our final solution in terms of theta has the sine of 2 theta. So we actually have to use another identity from trig, specifically the double angle identity. The sine of 2 theta equals 2 sine theta cosine theta. So based upon our triangle, we can see that sine theta is here, cosine theta is here, and we can plug these in. Well, also, this is 1/2 theta, right? Theta over 2 is 1/2 theta. Well, going back to our original substitution, theta equals the inverse tangent of x. And so using those several ideas, again, we have 1/2 tangent, or excuse me, 1/2 theta, and theta again is the inverse tangent of x, so that's the substitution for the first term. And then here we're just multiplying 2 times the sine of theta over the cosine of theta. And so we're multiplying, we have all of this over 2. We're multiplying it by 2, and then we have x over 1 plus x squared times x over the square root of 1 plus x squared. So we get x over 2 times 1 plus x squared. All right. Plus c. So you can see here sometimes these identities are going to be a little more involved than we thought. Our last example is a little bit confusing because it doesn't look like any of the patterns that we're trying to use for this whole section. But if you remember back when we started Chapter 8, we looked at some different manipulations that might be necessary to simplify things so that they would fall into a pattern. So what we're going to try to do is actually complete the square. This example illustrates a useful preliminary step that we did in 8.1. The integrand doesn't contain any of the patterns a squared plus x squared minus a squared, etc. that we have been using throughout this section. But if we complete the square in the numerator, we'll see that it does lead to one of those patterns. I'm not going to walk through the steps of completing the square. You should know this already. Completing the square in the numerator changes from x squared plus 4x minus 5 to x plus 2 squared minus 9. If we do a substitution with u equals x plus 2, notice that our integral changes now, and our du is dx. And notice we've also changed the limits of integration. In this case, it's really quite easy to change them. If x equals 4, then of course u equals 6. If x equals 1, then u, which equals x plus 2, would equal 3. 2 plus 1 is 3. And so in this problem, we're not going to keep going back. And in fact, as we go through multiple levels of substitution, it could get a bit hairy trying to go back from theta all the way back to x. So here we're going to follow through with changing our limits of integration. Now this integration is the x squared minus a squared, with a being 3, the square root of 9. And this calls for secant substitution. So we get u equals 3 secant theta, a secant theta, du would then equal 3 secant theta tangent theta, and the square root of u squared minus 9 would simplify into 3 tangent theta. I'm not going to walk through that substitution again. You can go through this and factor out the 9 and etc. and then secant squared minus 1. Anyway, all right, you can do that on your own. Once we plug those values in, we get 3 tangent theta in the numerator and 3 secant theta in the denominator. And notice here again, we're going to change the values for the limits of integration. Okay, these are values for u. Now we want to put them in terms of theta. So if u equals 6, then 6 equals 3 secant theta. Divide both sides by 3, and you get 2 equals secant theta. The inverse secant of 2 is pi over 3. And then the same thing, the inverse secant for 3 over 3 divided by 3 would give us 0. All right? Again, I'm not going to go through those. These are pretty straightforward. These are x values to u values to theta values, and you can figure those out even with as simple as your calculator. And then of course we have du, which was 3 secant theta, 3 secant theta tangent theta. We simplify all this, the secants cancel out, and we get 3 tangent squared theta d theta. We change this into secant squared minus 1. And so we can take the integral of both pieces, and so this ends up being 3. The integral of secant squared is tangent. The integral of 1 is theta. So we get tangent theta minus theta evaluated from 0 to pi over 3, which gives us this final answer of 3 times the square root of 3 minus pi. Again, there's some more similar exercises that I strongly recommend that you try. But this is just kind of a combination example showing you what we learned in 8.1, that preliminary step to make it look like the patterns that we're doing in this section for trigonometric substitution. You can see there's a lot of information that you're carrying with you from prior courses that is really vital as we get into these upper level math type problems.